So, let's talk time dilation. Here's a little disclaimer, though this one is actually more towards the realistic side than unrealistic, but still, disclaimer's a disclaimer. So yeah, read it if you care. So, time dilation, at least that's what I call it. I don't know if that's exactly the term for it, but that's what I'm gonna use. Time dilation is a shift in, I guess, the passage of time. So, time may be moving like this, and you're shifting how much it's moving. The way that I like to think of it is that, let's go with the theory that, for this example, let's go with the theory that time is a fourth dimension. This isn't a representation of a fourth dimension, at least an accurate one. There's no way a human, or really any three-dimensional organism, can think of a fourth dimension, at least not without being like exceedingly powerful in terms of brain. Big brain. Yes, I know how to English. Anyway, that's besides the point. Along this fourth dimension, let's just assume this is a fourth dimensional axis, we are moving at some rate on average. Alright, so for the sake of argument, let's say this is 1 second, and that's our unit here. This is almost our coordinate grid. So each of these is a second. And you can think of this as a vector, which if you've taken, I'm going to say algebra 2 or more, you can figure out what a vector is. Basically, it's just something that you can use to show that if I were to apply this vector to a point, it would put it here. Okay? Anyway, it's basically velocity or movement in terms of physics. So, from this vector, you can change to what extent it's moving. However, you can never change its direction, at least in this case. Usually vectors you can actually change out the vector by multiplying by a negative value, but in this case we can't do that, okay? And I will explain how you actually do this in a minute, but I want to make sure this is clear. Within mathematics, you can multiply vectors, you can make it negative and make it go this way, and stuff like that. But for this, we're gonna assume that some variable, which we're gonna reference x, is greater than 0 and is a real number. The reasoning behind this is that going backwards, which I will show in a minute, going backwards in time is not possible through at least using gravity, which is really the only way, at least that I know of, to change the passing of time for a certain area. You can't set it to go backwards. You can only multiply it by either a fraction. You can make it half, where x is equal to 1/2. You could also make it double the size, where x is equal to 2. Alright, it's not a hard concept, but I want this to be clear because it can get difficult at times. So, I'm gonna remove all this. So, now that that's out of the way, how do we actually change this x value? Well, it's pretty simple. Not really. So, let's start. We have really two cases how you would change it. You change time, first of all, I guess, by manipulating space-time to some degree. So if this is space-time, you either go in an area where there's there's negative mass, or you go in an area where there's positive mass. And it needs to be, you can, calculate by some means how much mass that needs to be. But you really have two main cases that you need to think of. Negative mass and positive mass. And I'm gonna use extreme examples for this to make it easy to demonstrate the point, but it does not have to be the examples that I give, and you will see what I mean. So, if you've seen Interstellar, I haven't, but I know a basic premise, to some degree anyway. I really know only this detail, but anyway. So, in Interstellar, they're like right next to a black hole, and 1 second next to a black hole is, I don't remember how much, but it's some ludicrous amount of time on Earth. I don't know if it's accurate, but for sake of argument, let's say it's 70,000 years. So, you have sped up time for the general region. Well, technically you haven't, but you're in the general region around this object of mass in which time is sped up such that an hour is now 70,000 years. And again, this is an extreme example, and I don't know if this is an accurate metric, but that's the point I'm trying to make. When when m is big, then x, the speed at which you're traveling along the fourth dimension, which again, it's not really how it works, I'm pretty sure, but it's again for the sake of making it easy to understand and making it, yeah. So x, the speed at which time is passing for us is big. So even though you're right next to a black hole, everything feels fine. If you were to actually look, you would be able to see millennia passing by in that way. So 1 second for you would be, let's just say, 2 seconds on Earth. It's not accurate by any means, but I want to make it have smaller numbers. Actually, no, I'll stay consistent, actually. 70,000 years. So you're moving 70,000 years per second, essentially. Which is kind of weird to think, but yeah, that's how it is. Now, let's say the opposite. We are next to some theoretical negative black hole in which you have a negative mass value, which theoretically is possible and is possible within UF rules. So you have some, I'm going to use green for this. You have some negative black hole which pushes things away at the same force a black hole pulls things in. So in doing this, now if you were to sit right here and somehow avoid all of the force pushing you this way, you would be traveling at 70,000 years for you. If let's assume this is the same force as our previous interstellar black hole. 70,000 years would be 1 second on a place with normal gravity. Okay? Meaning that when mass is negative, then x is small. And again, realistically, if you're trying to do this, no one's gonna ask you for exact numbers, because it's really quite hard to calculate this, and I'm not sure if it's even possible. But again, I want to make the concept itself clear so that anyone who's smarter than me wants to figure it out, they probably could. So, yeah. Negative mass, in summary, slows down time, and positive mass speeds up time. And to be clear, the actual feeling of time passing would be the same. 1 hour within that 1 hour within this area is still 1 hour, but the second you leave, now it's been 70,000 years. Again, I just came on using 70,000 years, that's my example. That's not an accurate metric by any means, but that's besides the point. So, here's our little conclusion thingy. When m, our mass, is negative, then x is small. Alright? When m, our mass, is positive, then x becomes big. If we get our vector here again, this vector now for x equals 2 becomes twice as fast. Now, 1 second in that area is 2 seconds in real life. You've doubled the passage of time relative to some arbitrary constant point. And if you're in a negative mass thing where x is now negative, not negative 2, 0.5, now time is passing at half the rates that it usually does. 2 seconds for you is 1 second on Earth, our relative point for now. So, the best way to get a accurate kind of reference point, if you need one of those, is when you're in an area where there is no gravity, or more realistically, there's a point where there is no significant amount of gravity that has any bearing on your measurement. Like, if you're in a place, there's technically gravity coming in from all the surrounding stars, but those are light years away. The gravity from them is minuscule. So for when m is equal to 0 or almost 0, then whatever your x value that you can find from that x is your reference point. That is our pure metric of time. That is how we know, okay, 1 second at this place is essentially our universal second. It's a relative value, but it is within at least that universe accurate. So, these are kind of our 3 things. Really, if you can kind of get this, the rest of it becomes pretty simple. And again, I know some of you guys haven't really done much algebra, haven't done much in that respect, so this variable might be confusing, but it is essentially just a placeholder value if you haven't learned variables yet, which hopefully most of you have, but again, just to be on the safe side. So yeah. And one thing that I kind of thought of and realized it wouldn't work, and I want to, don't want to have you guys wasting your time thinking of those things, which that kind of came out wrong. Like, I'm perfectly fine you're coming up with your own ideas and things like that. That I'm not saying don't bother thinking about it because I'm clearly the best, no. But just, this is something that I have thought of and I have figured out, and I know for a fact that's not how you can do it. You can never have x as 0. X never becomes 0. X never becomes negative. Because any amount of negative mass, it will still be a minuscule fraction of x, but it will still be, all it does is just essentially intensifies this effect. m is very negative, then x is very small. Same for the other way around. M is very big in the positive direction, x becomes very big. So, yeah. Really, you would, even at some mass of infinity, x still becomes infinity at that point. The passage of time is really small or infinitesimally small. Really big or infinitesimally small. Which leads me to one final thing before I let you go. What is the relation between positive, for some positive m, and then the inverse of that where it's that same value but negative now? So, let's say our mass here is 5. Alright? I'm gonna move this a bit. I'll put it here. And I know it's gonna be annoying, but it's fine. Here, actually, I'll just... There we go. So, our m is 5. That means, let's say for sake of argument, that makes x 10. Again, I don't know the relation between m and x. I just know this kind of relation. I don't know exactly how big, but let's just say, for sake of argument, when m is equal to 5, then x is 10. So, when m is equal to negative 5, then x will become 1 over 10. It is an exact reciprocal, essentially. The reason why is because, how should I explain this? In geometry, like, in space-time geometry, really, negative 5 mass and positive 5 mass, they have the same effect in terms of magnitude on how much they affect the passage of time. The difference is in which way do they expect. Do they make time slower, or do they make time faster? That is what's determined by this. The actual magnitude of the effect stays the same, which is why, you see, x, when m is positive, then x changes time, or multiplies the passage of time by a factor of 10. And then when m is negative 5, x divides instead of multiplies, the exact opposite, by 10 against our universal time passage metric. So yeah, there you go. Really, this is how time dilation works, at least within UF. If you have, as I'm hoping to make kind of a long-running way of working this, if you think something I said is wrong, you think I've said something incorrect, you want to correct me, you want to maybe give a new concept that I haven't given thought to, feel free to put it in the comments or whatever. I will, maybe not me because I don't run the channel, it's not mine, but I post videos anyway, but I will be checking the comments of my own videos. I will be keeping an eye, and obviously on the Discord, that's where I am a lot. So yeah, have any questions, anything of the like, you want to discuss science with me, Discord is the place to go, and if you can't do that, comments. And with that, I will let you continue your day. Bye.